In this first module of Chapter 9, Module 9.1, I cover different concepts and methods for estimating population numbers in the wild. Obtaining an accurate estimate of the number of individuals in a cohort or a population is clearly critical to biodemographic analysis, but obtaining these estimates can be difficult. For species in their natural habitats, there are a number of different methods to estimate population sizes, the examples of which are described here. Complete counts. Complete counts refer to the straightforward concept in which every member in a population is counted. This is often based on photographs. For example, waterfowl on lakes, seals on beaches, or elephants in open areas. Other methods, such as deer drives, can be used where all individuals must pass through a narrow area for counting. Will also provide a complete count of nearly all individuals. In studies with plants, complete counts are possible in species where an individual can be clearly defined. In other words, when the definition is not obfuscated due to clonal growth. In all cases where individuals can be easily identified and marked, longitudinal studies are the gold standard for demographic studies. Incomplete counts. An incomplete count involves counting subpopulations within one or more quadrats and then extrapolating to the entire population. Strip censuses, roadside counts, and flushing counts are examples of incomplete count methods. The basic model for estimating population size is based on the assumption that the ratio of population number in a quadrat to the quadrat's area equals the ratio of the total population to the total area. Here is the basic relationship where PT, AT, CQ, and AQ denote the total population, total area, quadrat count, and quadrat area, respectively. A basic assumption of this method is that individuals are scattered randomly across the study area. Indirect counts. Indirect counts use indirect signs of the number of animals present as indices of relative abundance. This method does not provide estimates of the number of individuals in the population, but rather can be used to show population trends, that is, increase, decrease, or stationarity. Examples of indirect counts including counting scats, fecal pellets, that is, or the number of nests or dens in a given area. Mark recapture. The use of marked individuals that are captured, uniquely marked, and then recaptured is a major technique that is used to monitor biological populations. Here I will briefly focus on how this technique can be used to estimate population size, and later I will provide more details on marking techniques and how this approach can be used to estimate survival. Mark recapture methods were first developed by Peterson in 1896 and later proposed by Lincoln in 1930, in his case to estimate ducks, and this is often referred to as the Lincoln-Peterson Index. The method involves capturing a number of animals, marking them, and releasing them back into the population, and then determining the ratio of marked to unmarked animals in the next population in the next sampling event. The total population, PT, is estimated by the formula given here, where M is the number of animals marked in the first trapping session, C is the number of animals captured in a second trapping session, and R is the number of marked animals recaptured in the second trapping session. Assumptions for this method of population estimation are that the proportion of marked animals captured in the second trapping session is the same as the proportion of total marked animals in the population, that each trapping session captures a representative sample of various age and sex categories from within the population, and that marked individuals do not lose their markings. Other assumptions are that the capture rate and the mortality rate for marked and unmarked individuals is identical, that marked animals mix randomly with unmarked animals, and that the population has no significant recruitment or ingress, that is, births or immigration, or egress, deaths or emigration. As an example, suppose 10 rabbits are captured and marked on day 1, that is M equal 10, and on day 2 the total captured is 20, that is C equal 20, 5 of which are marked, that is R equal 5. Then the total population is given here. If recapture data is available over multiple days, the frequency of capture method can be used. This concept is based on plotting the number of times individuals are captured versus the number of individuals captured each time. As an example, suppose over a 1-month period, the number of marked individuals that are captured 1 time, 2, 3, 4, 5, 6, and 7 times is 30, 20, 10, 6, 5, 3, and 1, respectively. These data are then fit to a statistical distribution to determine how many rabbits were never trapped, even though they were present. In this case, if we assume that rabbits are captured at random, the estimate of the number never trapped is between 25 and 30. The number never trapped at all but present is added to the total number captured to give the frequency of capture estimate. In this example, the population size estimate is slightly over 100 individuals. That is the sum of value of all the bars. Hunting effort. A method related to the frequency of capture method is referred to as the Delury method, based on the concept that the number of animals killed per unit of hunting time is proportional to the population density. By plotting kill rate, that is animals killed per day, versus total kill, it is possible to get an estimate of the total population by extrapolating the line to the x-axis, where the intersection is the estimate of the total population. Assumptions of this method include that the population has no immigration or immigration, that is, that there is an identical hunting risk for all animals, that variable hunter skills can be quantified and averaged, and that hunting is done individual. Change in ratio method. Originally applied to deer populations, the change in ratio method is used to estimate the size of a population when a population can be divided into 2 classes and when the ratio of these 2 classes changes due to a selective removal from the population. The classes within the population can be based, for example, on sex, size, age, or maturity. An example application using sex status is given here, where N1 and N2 denote the pre- and post-hunt populations. T denotes the total kill of both sexes. F, the total females killed, and P1 and P2, the proportion females pre- and post-hunt. The formula for estimating both the pre- and post-hunt populations is then given here. Inserting numbers for each of the 4 parameters, that is T, F, P1, and P2, into these formula to obtain N1 and N2 is simple and straightforward. This ends this first module of Chapter 9.